Hi, my name is Spencer Janik, and I'm a product manager on the AWS Cryptography team working for the Key Management Service. I'm joined by Paul Radulovich, my colleague, who will introduce himself a little bit later. And today we're covering the Busy IT Manager's Guide to Encryption. We have a couple of talks in this series, including the Busy Engineer's Guide to Encryption, which is available as an open source exercise that you can check out on GitHub. It's pretty great. But this series, and this particular talk, is a follow-up to a related session that Becky Weiss conducted last year in 2019 at the Reinforce conference called The Fundamentals of AWS Cloud Security. So I'm including a link here. And in that talk, she identifies three fundamentals: IAM, which is Identity and Access Management System, VPC and network controls, and cryptography as the three fundamentals of AWS cloud security. And she uses Key Management Service as her example. And Becky in that talk she represents the identity and access management team. And in her talk spends about 80% of her time talking about IAM, which is the identity and access management system, as well as VPC and networking controls. And so we think that's about the right breakdown. And we wanted to make sure today that we cover the cryptography angle a little bit more deeply. So our agenda here is going to first review security and defense in depth to see how those are related. Then we're going to talk a little bit about cryptography and security and compliance to talk about how you can use cryptography to meet your compliance objectives. Then we're going to talk about identity and cryptography, the relationship they have with each other. And really, identity and cryptography reinforce and can supercharge each other. So identity without cryptography can be weak, and cryptography without identity controls can be weak. So using those together is really the way to go. And lastly, Paul is going to walk us through building an application using the different AWS cryptography services. So we can learn a little bit about each service and the role that it can play within your AWS cloud environment. So first question is, what is security? So we talk about it a lot, but we rarely define it. We think about security is in terms of reducing risk. And there are two primary risks that we're concerned about. We're concerned about exposure of our data. We have all sorts of data with different levels of sensitivity, and we want to make sure that only the parties that should have access to the data actually do have that access. So we're worried, we're wanting to be concerned with the risk about exposure of data. The second risk we think about is loss of control. That we have an application that does something, and we want to make sure that unauthorized parties don't get access to control that application. So when we think about those risks, there are two further categories that they can fall into: inadvertent risk, which is something happening by accident, or malicious risk, which is something happening on purpose. So keeping that in mind, one of the primary ways that we ask customers to meet security requirements is by reducing the complexity. And so there are a couple common patterns that once you learn them, you can reuse throughout AWS. And even though we have many services, you'll be able to reuse a lot of common patterns. And so the key here is what we call internally reason. So as a human, presumably you're human. On the internet, no one knows if you're a dog, but presumably everyone watching is human. You have the ability to reason about not only make moral judgments, which we're going to leave as beyond the scope of this talk, but also make judgments about the way that systems function. So the more complex a system is, the harder it is to reason about. And so we think that identity is a great way to improve your ability to reason about a system. If you very clearly and crisply define the identities of a system, you can reason about it more easily. We'll talk a little bit more about that in a minute. An AWS concept that we talk about with customers a lot and have in our documentation is defense in depth. So this comes from the Middle Ages and roughly, and it comes from the concept of defending a castle. Let's imagine that our application and our data is represented by this castle. So having the castle walls are great, but if the attackers can come right up to the walls, then there's a lot that they can do. So we like to build additional layers. First we build a moat, then we build out structures, etc. So these layers in the cloud can be one of the first ones that you consider is physical access. One of the reasons that AWS is popular with customers is because we have strong controls that prevent physical access to AWS data centers, which you can think of as availability zones within the regions that you use. Each is independent. And one thing that is great about AWS control of physical access is I've been at AWS for longer than 2 years, and I still have never seen and don't know where any AWS data centers are. So we have really strong controls, not only that keep them private, but also that keep them physically secure. The second layer that we're going to add here is network security. So by dividing the components of our application or the components of our AWS cloud environment into multiple networks, we're able to control the points of ingress and egress to those networks so that we can have a better understanding of which entities are accessing our data and when. Building on top of that, we have AWS IAM, Identity and Access Management. And we think, again, this is where you should be spending about 80% of your reasoning time when you're setting up your system and thinking about who are the identities that are going to access my data and my systems, and how do I want to define them, and who gets access to use those credentials. And then people often say that cryptography is a last line of defense. So I put it as the last circle here, but we don't necessarily think about it as the last line of defense. We think about it as an additional layer that you can use that increases the defensibility of your application or your environment. When used in conjunction with IAM and other controls, cryptography can be an additional layer to protect your data. So you likely have seen this shared responsibility model chart before, where at the top, you, the customer, is responsible for security in the cloud, and at the bottom, AWS is responsible for the security of the cloud. So at the very bottom, we have AWS regions that contain availability zones. We also have AWS edge locations. We are responsible for the security of the hardware in those locations, and a number of other services that AWS makes available. But if you look in the customer portion, at the bottom row, you'll notice that we highlight client-side, server-side, and network traffic encryption. So a lot of our security conversations happen about customer data at the top row, or platforms and applications that customers deploy and the operating systems they're using, et cetera. But one thing that doesn't get a lot of airtime is how to deploy client-side, server-side, and network traffic encryption, and what the difference is between these different components. So why would you encrypt, and why would we include this in the customer side? There are three reasons that you'll want to encrypt your data. The first is it keeps your data confidential. And this is a property we talked about a little bit earlier, that you want to make sure that nobody except the intended party has access to the data. The second, and we see this as a very common reason that customers use cryptographic controls, is that it can help them demonstrate compliance. Regardless of the industry you're in, it's likely that there is some kind of compliance framework that would require you or strongly suggest that as a developer, you integrate controls into your application that prevent exposure of data or loss of control. Cryptography is a frequently used technique to demonstrate that you're meeting compliance obligations. And lastly, this one is a little counterintuitive, and I even got a little bit of pushback internally when I first put it in this presentation, is that I think judiciously applied that cryptography can actually improve your agility. And part of the reason is because of the reasoning that people can do that we had a little bit earlier. If you know that your data is protected by access to a key, in many cases, it allows you to move more quickly because you can then understand where the key bottlenecks or choke points are in your security threat model. So this is the last series of three that we're going to give you here today. And there are three properties that security has that you can think about and reason about when it comes to your threat model and your security environment. And those are confidentiality, integrity, and authentication. Let's run through them one by one. Confidentiality is the property we spoke about earlier of making it so that the data is unreadable by anybody except its intended recipient. Integrity is the cryptographic principle that allows us to determine that the data that we're reading is the data that was encrypted, that there haven't been any changes or modifications made to the data since it was sent. So we would often say it's bona fide. And for those of you who don't have experience with Latin, it comes from the Latin literally with good faith. So if something is bona fide, it's the genuine article. How do you know that the encrypted file that you're accessing is really the same encrypted file that was saved there? That is the integrity property of cryptography. And lastly, authentication. And this is an important and often undersung principle of cryptography, that you want to be able to verify that not only has the file not changed since it's been saved there, but also you need some way to prove the party or entity that saved that file there is who they claim to be. So cryptography provides a mechanism to authenticate individual objects or individual connections or sessions to say, this is the party or this is the entity that I think that they are. It provides a way to prove identity. So let's talk a little bit about an example of how this is deployed in practice. And Paul, at the end, will get into a little bit more detail about how an application could be built and the application architecture behind this. But let's say that there's a user and they want to, on the left, and they really want to access a file in this S3 bucket on the right. So a user in AWS is commonly referred to as a principal. It's an entity that is able to have a set of credentials that let them interact with AWS. And so there are a couple checks that have to be made. First, the user who's attempting to use these credentials actually has to have access. So IAM will check the credentials of that user when they first attempt to gain access and authenticate to the AWS system. And then in some application scenarios, the user will have to confirm that they're exiting a particular environment using a particular endpoint. So at that point, there is a credential check to make sure that the user has permissions to egress from that endpoint. And then when they're making a request from a particular bucket, the permissions are also checked to make sure that they have access. But let's say you want an additional level of control here, and you want another check to make sure that this is the appropriate user and this access should be granted. First, before we get to what that layer is, let's talk a little bit about how encryption works in AWS. So originally, as businesses started to collect data, they realized some of it was sensitive, businesses and other organizations. So they used a key, a cryptographic key, to keep that data confidential. But over time, these businesses and organizations started to collect more data, and then that data started to increase exponentially. So all of a sudden, this key on the left that encrypts all of this data has become very important, because if that key were ever to leak or become inadvertently or maliciously exposed, it could be used to decrypt any of that data. So perhaps to reduce the risk of exposure of that key, you can create multiple keys and use keys to secure different categories, classifications, or customers of data. So that limits the damage that exposure of any one of those keys can cause. You can take this to its logical conclusion and say, okay, well, if I want to limit the amount of exposure or harm that the release of any one key can cause, maybe I should use one key for each individual piece of data. And at AWS, we think that's a pretty good way to do things. And that turns out to be a lot of the way that we use cryptography internally. So businesses then are faced with the challenge of what to do with all these keys, or organizations. And so the first idea that we had was let's put all of these keys that we call data keys, because they protect individual pieces of data, in a database. That way, we can have a perimeter around that database. So if a user ever wants to access a key to decrypt data, we'll be able to verify that they actually have access and control access around that perimeter. That's a great story, except once we have that database of keys, it raises important questions. How do we back those keys up? If we have to create additional copies of the database, that means there are users that have access to the backed up copies of the database. And as you start to accumulate millions or billions of objects, you accumulate similarly millions or billions of data keys. And managing all those keys can become really confusing, and you can get a bit of a key mess on your hands. So maybe we can encrypt the key and store it with the object itself. That way, we don't have to worry about storing the keys separately from the objects. We can store them together. In AWS, this is a technique that we use, storing encrypted data keys with the data that they protect, that we call envelope encryption. Let's see why. So we have a root key that encrypts the data keys that protect the object. But if we wanted to look at one of these objects, if we looked inside this object, we'd see the encrypted data key and the data. But when we wanted to decrypt it, we might wonder what key was used to encrypt this data key. So I can decrypt it and then use it to decrypt the object. So we attach some metadata inside of our envelope. If you were to look at the file structure, you'd see at the header of the file there was some metadata saying which key was used to encrypt this data and other information about it. You'd see the encrypted data key, and you'd see the encrypted data. So then that raises the question of, so we have all these keys and we're encrypted, and they have envelope encryption to protect our data. How do we protect this root key? Well, if you've been following along so far, what you might think is, oh, well, let's use a key to protect that key. And then let's use another key to protect that key. But this could continue ad infinitum. There's no end to the key hierarchy that we're creating here. So at AWS, the thing that we've developed that we think is generally a good thing to consider when trying to protect this root key is actually to put it inside a service that's highly available and highly durable, so that AWS can take care of backing up and managing access to this key. And this is the system that we call the AWS Key Management Service. So whenever an object needs to be encrypted, you can call the AWS Key Management Service, generate data keys, and create an encrypted copy to save with the file in an envelope. So it functions as a durable, available root of trust. So we talked a little bit about policies earlier, and so you're probably familiar with IAM policies on the left, where it's something like you have a version statement, and then you would say for a particular user, although we don't have a principal in this particular snippet, for a particular user, we would allow the actions of listing the keys that are available in KMS and listing their aliases that can be used to call those keys. So you might wonder, well, what then does a key policy look like? And a key policy is identical fundamentally. It has a version, a statement with an effect of allow, and actions like list keys and list aliases. But rather than happening at the level of access to KMS to say, does the user or principal attempting to make the call have access to list keys, you can also give a permission to list the key of a particular key. And so using a key policy in this way can be pretty powerful. And there are two ways that I'd like to highlight the power of this. The first is you can separate administration and use. So here, when we're looking at the administration of a key, you can see on the right side in the key policy that you could allow an individual user to list the aliases for a key, create new keys, describe keys, enable keys, and a variety of other functions that you would need to administer a key, including deleting a key or tagging a key with a particular tag or scheduling the deletion of a key. And this is really useful for organizations that want to have central control over keys because it allows you to specify one party or more parties that have the ability to control the keys separately from using the keys. That way, you can have a detective control of when a party tries to access the key that you don't expect to perform an administrative function, that you can throw a particular alert. On the other side of that is use of a key. So you can use a key to encrypt directly or decrypt directly, or you can use a key to generate a data key pair so that you can perform client-side encryption, so encrypting with your application that Paul will talk about a little earlier. We also have a permissions mechanism that is a little bit beyond the scope of this talk on the bottom here, which is allowing the attachment of persistent resources. So if you'd like to create an encrypted EBS volume, for example, using a KMS key, you can create the permission in a policy to allow EBS to create a grant on its own behalf to encrypt EBS resources. Another interesting way that you can use key policies to divide permissions or separate duties is separating encryption and decryption. So on the left side is a brief statement that would allow the use of encryption or decryption for using a key. And on the right side, you can see that there's the ability to decrypt. So by separating one component of your application, let's say the user-facing data collection layer, from decryption, which is, let's say, a layer of your application that you use for processing data, you can separate duties. Then that allows you to make sure that the users who are attempting to encrypt data have permission, and be very permissive about who has the ability to encrypt data, but be very restrictive about who has the ability to decrypt that data, or vice versa, depending on the needs of your application. So key policies are a very powerful mechanism in that sense. Let's take another look at this defense in depth model that we were talking about earlier, where you need to add in a new layer of defense. By adding in a key policy, it provides additional opportunity for you to develop policies that can help your application determine who should or should not have access to encrypting or decrypting data. In this case, fetching an object from an S3 bucket. So this is a form of what we call server-side encryption. So over 60 services in AWS now support integration with KMS to provide server-side encryption. And in this particular example, we were looking at S3. So let's stick with S3 and take a look at the two flavors of server-side encryption that S3 provides. SSE S3, which is server-side encryption S3, or server-side encryption using KMS. So a traditional server-side encryption using S3 call is just a checkbox that you can provide to say, should this object be encrypted? If it is, you'll notice on the left side, we have our envelope that's stored in S3. And when a user requests the object foo, S3 will make a request to a key, decrypt the data key attached to that object, use that data key to decrypt the object, and then pass the file to the user that requested it, foo, for users who have permission to access it. But if we add a second step of using a SSE-KMS and the key is stored in KMS, you'll notice that the permissions check and the boundary moves out from S3 entirely to KMS. So now if a user requests the object foo, S3 has to query KMS and say, does this user have the ability to access the key that encrypted the data key that secures the file? Part of the advantage here is the permissions check, but another advantage is you also get CloudTrail logging. So CloudTrail can generate a log of who requested access to that key and when, and whether it was denied or approved. That way, you have access to a log that you can use to track access historically. Looking here at a chart version, you can see that the permission model for SSE S3 just uses an SSE S3 to perform the permissions check, and the logging is also done at the S3 level for SSE S3. For SSE using KMS, you can see that the permissions model includes a check at S3 and the KMS level, and the logging happens at both the S3 and the KMS level. This granularity gives you more flexibility in determining how you'd like your policies to be created and what you'd like them to do. So when you look at the credentials that you have, it's actually, let's focus on this user for a moment. So who is the user and how should we think about them? Well, the user could be an operator, an IT manager who's checking a configuration of something that's deployed to maybe collect promotion feedback, or an engineer who's working in the operations or developer team that needs to resolve some sort of emergent issue. But by understanding these as particular identities rather than individual users or individual components, it really improves our ability to reason about should they or should they not have access. But there's another class of user as well that include machines, like an app environment. Maybe a resource in my front end needs access to this particular resource. If a front-end resource is requesting something that's unexpected, that could be a good opportunity to trip some kind of alert or alarm. It could be a server function. So I could have a server that spins up every once in a while to perform some particular action, like making a backup or processing data in a particular way. And we could detect things that were unexpected for that type of identity if we identified it correctly. Or it could be a serverless function, like a Lambda that's spun up to perform some sort of action. But once we understand these identities and give names to them, it becomes a lot easier to reason about how we develop a policy that includes permission to provide or deny access to that particular entity. I'd like to talk about each of the individual KMS or AWS cryptographic services to make sure that we've covered each of them and the use that they can provide, which Paul will get into a little bit more detail about later. So KMS is a highly available and durable root of trust that can store your root keys. It's focused on the confidentiality and integrity properties of data and generally uses AWS IAM to perform authentication functions. But the strongest key in the world isn't useful if you can't access it, is one thing that we like to say. So KMS is focused on that high availability and high durability for those individual keys. So as I mentioned earlier, it integrates with over 60 AWS services. So pretty much anywhere where you'd like to store data in AWS, you can use a KMS key to protect that data and have access to granular logging. The next service I want to talk about is AWS Certificate Manager, which is also a highly available root of trust. You can use it to drop certificates and manage certificates, which you might want to do in like a load balancer that Paul will be talking about in just a moment. It's focused on the authentication properties because the fundamental benefit of certificates is that, and its certificate management, is that it allows you to have a durable identity store. So you can use cryptographic authentication properties to know that either the entity on one side or another is who they claim to be. And it also supports confidentiality and integrity properties, but it's not the primary focus. AWS Secrets Manager is a highly available data store that you can use to distribute secrets within your environment, whether it's OAuth tokens or credentials or database passwords. Secrets Manager is integrated with KMS, so you can use a KMS key to encrypt and protect your secrets. And it also has support for rotation. So if you need to rotate credentials, you're able to do so with Secrets Manager natively. AWS CloudHSM is a single tenant piece of hardware, and it's typically used for customers that helps meet some compliance. So the compliance requirements that customers may be subject to is, for example, access to a FIPS 140-2 level 3 validated hardware security module. And if customers are subject to compliance requirements like that, AWS CloudHSM can be useful to help meet those requirements. In some cases, AWS KMS provides a feature called custom key store that can be used in connection with CloudHSM to provide an AWS KMS interface to a CloudHSM backend. But in general, we recommend ruling out the use of AWS KMS before considering CloudHSM. Now I'm going to turn the presentation over to Paul, who's going to walk us through the process of building an application using these cryptographic services. Paul?
Thank you, Spencer. As Spencer mentioned, my name is Paul Radulovich. I am a software development manager within AWS Cryptography, and I work on our crypto tools team that does a number of different things, including working with the different AWS services to integrate with KMS, as well as building out some of our open source libraries for encryption. So as Spencer mentioned, we're going to talk about an example scenario here. The one we're going to go with is a pretty generic secure web application. It's a pretty common one that everybody has. So the different components are going to be cloud servers running a web application. For that, we're going to use Amazon Elastic Compute Cloud, so EC2. You might be running one of a number of different web server applications like Apache, Nginx, countless others. We're also going to store some information in a MySQL database. For that, we're going to use Amazon Relational Database Service, RDS. We're going to have an object store. We're going to use Amazon S3 for that. And as Spencer mentioned, we're going to also incorporate some third-party connections, maybe using OAuth tokens. So let's say you want to talk to a code repository like GitHub and Bitbucket. So this is what our very simple application looks like. You'll see in here we've got just kind of your generic components. Our website is foo.com. It's a secure website. It's one of our favorite websites, and you'll notice a couple of different boundaries here and connections. We also have CloudTrail, which is where we're going to get all of our logging. All of our actions across our services are automatically going to show up there. So let's talk about the different risks that we have within this application. They're kind of countless, but the ones that we're going to focus on today. There's always S3 object exposure and access. We want to make sure that the objects in S3 are only accessible by parts of our application that should have them. And then on our web server itself, there's a number of risks and important credentials we have there. We have our actual IAM credentials and tokens. We use those to talk to the different AWS services from our web server, for example, RDS and S3. We're going to be storing our third-party OAuth credentials. We have our database credentials. And since we're a secure web application, we have to store our SSL certificate and control access to that as well. All of those things, there's a number of ways I can get there, but you're going to have console access to the server as well for both maintenance, configuration, all of those things. We also talked earlier that the kind of second layer of, or the second ring of our defense in depth was network, right? And so we're not gonna cover these today, other than the fact that we have our application in a virtual private cloud, our VPC, for networking, and the individual components are within their own security groups. If we were to dive into this would probably be a number of additional talks, but we are using best practices and putting our applications within these containerized networks. So all of these credentials that we have, we're storing them somewhere. That's kind of where our risk comes from. For our console secure shell access, we're not using username and passwords. We're thankfully one step beyond that. We're using public and private keys, if you're familiar with that. So we've got our public keys stored in an authorized key file on the server. Anytime we have someone new working in our environment, let's say a new contractor comes on or a new employee comes on, if they need access, we're going to have to go and distribute those keys across all of our instances that they need access to. The SSL certificates are stored as a local file. Again, we're going to keep our database passwords, our OAuth tokens, our AWS tokens. All of those are going to be stored locally. Our objects in S3, it would make sense. You always want to have some form of server-side encryption. We're using the base version that S3 has. And then we're also going to have some external storage. So for our EC2 instances and RDS, we've got some unencrypted volumes, right? So the first thing that we're going to change about our environment here is you'll notice that we've added a couple additional components. So we'll start with our shell access, right? So for SSH, we are now using EC2 Instance Connect. Instance Connect allows us to couple the console access of our servers to an IAM identity. It allows me to go and say the user or the role that Spencer has is allowed to console into all of my web servers, or maybe he's only allowed to console into my instances talking to database. And just in this case, it's actually both. One of the other cool things we can do, if you're familiar with tags across AWS resources, we can do tag-based access control. So I can say Spencer is allowed to SSH into any instance where the tag is development, because he's new to the company. I trust him on all my development servers, but maybe not quite on all of my production servers yet. In addition to being able to control access with that level of granularity, we now no longer have to worry about not only adding access to instances when Spencer onboards, but if Spencer happens to leave, we now no longer have to go out into all of our different servers, remove his public key from those servers. We can just say that his IAM role or user no longer has access to connect to those servers. Super powerful feature there. The second thing we've done is you've noticed we've added an ALB, which is an application load balancer here. You'll see the red dotted lines are our security groups, and we do have our VPC there. So our application load balancer is put in front of our web server. This does a number of things. First, it actually allows us to do just what it sounds like, load balance. If our application grows, because we're incredibly successful, we have a ton of traffic coming in, we can dynamically grow the number of servers behind it. The application load balancer can spread the load across all of those different servers. An added bonus feature, or actually maybe not a bonus feature, maybe one of the primary features you might want to use in application load balancer is its integration with Amazon Certificate Manager, ACM. It is incredibly easy to go into ACM, create a certificate for my domain. In this case, I'm going to do a wildcard certificate for foo.com, which is going to allow me for www.foo.com or login.foo.com. I'm going to do some form of validation. I could do it via DNS. And I'm going to tell the application load balancer, I want to use that certificate from ACM. Behind the scenes, ACM is using a KMS key to encrypt your certificate. And the only way that you can decrypt that private certificate is with an integrated service. So in this scenario, the application load balancer has permissions to decrypt that certificate, which can never be exported. And that's another important feature. Earlier, when we had it on our instance, let's say someone who has access to the instance, either maliciously or accidentally, they're backing up a directory. Part of that directory happened to be the private certificate for your SSL. Now it's on their desktop. Let's say they're backing up their desktop to some form of online storage, or they've happened to put in a directory that they're putting into a code repository. It's a pretty easy way for you to accidentally leak your certificate, and then that's going to get rid of that entire authentication aspect. So now it's completely secure, can't be exported. We can control access to it via KMS. And once again, we've got, our HTTPS foo.com is secure. So if we go back to our table here, we've removed two of our risks. Again, SSH access, we've moved to Instance Connect. We're using ACM, and now we've brought the Key Management Service into the picture for encryption keys. So we've still got a number of other risks here. Let's see if we can get rid of more of them. So here in this diagram, you notice that we've added Secrets Manager. Spencer mentioned earlier, it's a highly available data store for secrets, just like it sounds like. So the first thing that we've done is we've taken our OAuth credentials. We're no longer storing them in, say, a local file or a local database on our EC2 instance, but we've moved them to Secrets Manager. And this allows us to only or maybe pull them from Secrets Manager when we need them. Let's say our application stores a number of credentials, so whoever's logging into our application can connect to their particular GitHub repository or Bitbucket repository. We want to keep those tokens safe. Behind the scenes, Secrets Manager is using a KMS key. You can tell it to either use the default key or you can tell it to use a specific key within KMS that you can control the key policy. Right? And so you may say that only the web servers have access to decrypt this secret within Secrets Manager. Additionally, you'll see that we've moved our database credentials from the EC2 instance to Secrets Manager as well. There is a pretty tight integration between RDS and Secrets Manager that not only allows you to store the password there, or have passwords automatically created in Secrets Manager when you bring up an RDS database instance. But on top of that, as Spencer mentioned, you can actually rotate your secrets. So let's say you have an internal policy that requires you to rotate your database secrets every 30 or 60 days, or maybe even 7 days. If you store them in Secrets Manager, you'll rotate them within your database instance in RDS, and you'll rotate them within Secrets Manager as well. Then when your instance needs to connect to the database, it can pull those credentials from Secrets Manager. Again, only if it has permissions to the underlying KMS key, and decrypt it at runtime when it needs it. So you'll also see on the right side there, earlier we brought in IAM because identity has now kind of become a crucial part of our architecture here. So if we go back to our risks in our table, we've moved our database passwords and our OAuth tokens. Secrets Manager, we're using identity now. Same thing as SSH access, we're using identity now to control access to all of those things. All right, so the next step here we're going to talk about is we've got our S3 objects. Before we were using SSE S3, which is that the generic encryption within S3, and so now we're using SSE-KMS. So all of the objects that I'm writing and reading to my S3 bucket now are using a KMS key for encryption. And as Spencer showed in a diagram earlier, when I go to get that object now, not only do I need access to the bucket and the object itself, but I need access to the underlying encryption key within KMS. Again, you have the option to use the default encryption key, or you can specify your own key that has granular permissions that you yourself can set. You'll also see that our EBS storage, or elastic block store that we have connected to our EC2 instances, as well as RDS's underlying storage, we've now integrated with KMS by encrypting those volumes as well to make sure that they're encrypted at rest. And that's generally, in my opinion, a good practice, and I can't think of any reason not to encrypt my storage at rest. So it's something that I would suggest that you're always doing. And the last thing that we have is you'll see that we've given our EC2 instance a role. Before, we had our credentials on the instance itself. Again, we need the processes on the instance to be able to talk to RDS. We need them to talk to S3, Secrets Manager, all of these different services that we have as components in our architecture. So now what we've done is we've taken those credentials off of the instance. Again, we wouldn't want them to somehow be exported, say someone who had SSH access, again, either maliciously or accidentally backs up a directory. Again, you find your credentials now in a GitHub repository, and now someone can log into, basically have the identity of your instance outside of your architecture, outside of your network, and access your resources, say in S3 or RDS, which you wouldn't want. So we're using an instance role now, and in IAM, we can go and add and remove permissions as we go along, and add and remove different components of our architecture. So we can also scope it down. We can have different instance roles for different instance types. Again, the web server might only need to process data and write it to S3, but may need to be able to modify the tables in our RDS databases. And all of these things can be added and taken out of your policies. So that covers all the things here. Let's keep going. So we've eliminated all of these different risks now. Again, we're using IAM and the instance role for our access tokens, and we're using KMS within our server-side encryption encrypted volumes here. Spencer did mention that there's a use case where you might want to have a CloudHSM. The CloudHSM will be the first ones to try and dissuade you. The CloudHSM team will be the first ones to try and dissuade you from using a CloudHSM. The majority of use cases, KMS is not only more than sufficient, but actually the preferred method for a root of trust for your encryption keys. But let's say you have a compliance or some very, very strict policy that requires you to have full control of your root of trust and your encryption keys. While you could use the CloudHSM on its own, and you wouldn't be able to take advantage of a lot of these server-side encryption integrations across all of our services. There is something called the KMS Custom Key Store, and that allows you to connect your CloudHSM cluster or instances to KMS. And the benefit of this is that now to all of these services like Secrets Manager and S3 and RDS and EBS and everything we've got here, it looks like a KMS key. But behind the scenes, KMS is pulling that root key, that root of trust from a CloudHSM cluster. One of the added benefits, in my opinion, on this is down the line when you either realize or your requirements change such that you don't need a CloudHSM cluster, you can remove all of the administrative tasks, you can remove the complexity of your architecture by removing the CloudHSM and using keys that are from native KMS itself. So again, here we've kind of brought in the custom key store, again, only for a specific requirement for control of the root of trust. So we also have a number of other services, tools, and libraries in AWS Cryptography that you can use. We've got the AWS code signing for Internet of Things. So if you have an IoT device, there's code signing, which allows you to authenticate or prove that the code is what it should be. We have an open source TLS implementation called S2N. It was designed to be small and fast and simple to integrate. If we go back to the shared security model on that lower layer of the customer side, we talked about server-side encryption, we talked about client-side encryption, and then we also talked about network encryption or encryption in transit, and that's where S2N could be used as well. For encryption at rest and client-side encryption, we've got a number of different libraries and products. We have the AWS Encryption SDK, which is a client-side encryption library. It's currently available in Java, Python, C, and JavaScript, as well as an encryption command line interface. For DynamoDB, we have the DynamoDB encryption client, and I'm going to go into these two a little tiny bit more depth, which is available in Java and Python. And we have the S3 encryption client, which is built into a lot of the AWS SDKs themselves. For new applications, unless they are specific to some of the large data lake applications that may use some of our services like EMR or Glue, I would suggest going with the encryption SDK. But if there are, like I said, some applications which require and can only decrypt the S3 encryption client, you may want to end up using that. So like I said, let's dive a little bit into the AWS Encryption SDK. So the Encryption SDK is not only a set of APIs, but it's also a data format for encryption. The reason that's important is that it allows for interoperability across implementations. For example, if you wanted to encrypt data with Java but decrypt it with Python, which we're going to see in a second, you could do that. Or if you wanted to encrypt in your browser, we have a JavaScript browser version as well. In addition to that, because it's an open source library licensed under Apache, you could create your own implementation as well. That's why we have that data format. You could create your own library. Let's say you have your own little language that you want to do it in. You could do that as well, and you could be interoperable and compatible. It's also a simple interface to have KMS compatible envelope encryption, which is what Spencer spoke about earlier. It's where you're going to keep the encryption key with the data and the metadata itself. One of the other big benefits is, and also with being open source, it uses community vetted primitives. So we're not using an encryption library that low-level encryption standard that we've come up with or is internal only to this SDK. We're using community vetted standards that are in the open community. We've also made it so that you can use multiple key providers. Obviously, it works very well with KMS, but if you wanted to go out there and connect it to any of your other specific key management services, you could. And if your application requires data key caching, we have that capability built in. So I mentioned that the DynamoDB encryption client, which is slightly different. This provides client-side encryption specific for DynamoDB, which is one of our databases in AWS. It allows for interoperability, again, between the Python and Java implementations. We always want that to happen. It's very important to us. But in addition to what the encryption SDK would do, it also offers integrity and authenticity, on each item, and confidentiality on each encrypted attribute. So it's going a little bit deeper and making sure that each of your entries in the database are exactly what they should be. You're not modifying any individual item or attribute of your, I should say, your items. One of the limitations, though, is if you have a primary key in your database, so let's say that's an ID of your database records, or probably a horrible idea to do it, but like let's say if you had it by social security number or something like that, you would not be able to encrypt that primary key or any of the other indices, which is how you search within your database, I should say. And again, the attribute names for the table can't be encrypted. So you can't encrypt the fact that this field is called first name and the next field is called last name. So let's look at a small sample custom application that we need to process personally identifiable information. Again, super simple here. We've got two different processes. One is going to create some artifacts, some files that we're going to store in S3, again, using server-side encryption with KMS, and another application that just needs to process it. Again, we're within our virtual private cloud. We've got our security group set up. We've got what looks like a driver's license there. So we're going to put the encryption SDK in the mix here. On the side where we're processing this data, we're using Java. We're going to encrypt the data client side. For that, it's going to reach out to KMS and get a data key that it's going to use. The next step is to store the encrypted object in S3. Again, we're still using our server-side encryption, but we're also going to do client-side encryption in this case here. Now we've got our consumer, which is going to read the encrypted object from S3. And again, it needs permissions to not only the bucket and the object within S3, but the permissions on the KMS key that was used to encrypt that object server-side. Oops, I keep going the wrong direction, sorry about that. And we're going to now decrypt the data client side, which is going to reach out to KMS and decrypt the necessary encryption key that was stored within our envelope. One of the other things that's important to note here is we're able to scope down the permissions. Spencer mentioned earlier the division of not only administrative and maybe operational permissions within KMS, but splitting the encryption and decryption. So in this example here, our Java, the instance where our Java encryption SDK is running, would only need permissions to generate data keys for KMS and would never be able to decrypt those objects after it's encrypted them. And our Python side would need decrypt permissions, but in this case, not necessarily need the same permissions to encrypt. So those are a couple of examples that we have. Just wanted to go through there for you. So what's next? Well, honestly, I would say go and create a KMS key in your account today and use it with one of those 60+ integrated services. As of yesterday, I believe the number was 63 services, and we're adding more and more every week. The easiest place to find all of these services is to go to the link that you see there. It's the main KMS link within AWS. Go to features and you'll see a section that talks about service integration. So with that, I just wanted to thank everybody for joining us today, and I hope you've learned something, and I hope you go out and create great things.